Welcome to my complete vectors tutorial here on YouTube and Receive Sense. It's a complete A to Z tutorial on this topic. Hope you find it helpful. So, physical quantities are divided into two groups, scalar quantities and vector quantities. So, scalar quantities are quantities that only have magnitude but no direction. So, let's say that 8 meters, 21 centimeters square, 7 kilometers per hour, and 5 seconds. They are all examples of scalar quantities because they only have magnitude. There is no direction here. They can be completely defined by a single number, which is the magnitude, an ordinary number, then with its appropriate accompanying unit. So in this case, the unit is meters, which is length. Here is centimeter square, which is area, kilometer per hour, which is speed, and 5 seconds. Here, seconds, it's the unit. So these are all scalar quantities. Moving over to vector quantities. Vector quantities are physical quantities that have both magnitude and direction. You cannot completely define a vector by stating only its magnitude. You must also specify its direction. So a 7 kilometers per hour due north will be a vector because you have specified direction, which is northward, and weight is also a vector quantity because it is directed downwards due to acceleration due to gravity. And examples of vector quantities are force, velocity, acceleration, and weight, etc. Representation of vectors. A vector can be represented by a line with an arrow always showing the direction. And in this example, the vector is AB, which is the line. It's moving from A to B, so it's shown by this unit vector. The direction is shown by the unit vector. We'll get into more details about unit vector in the next couple of pages. And so the unit vector in this diagram is denoted by the small letter or lowercase of a, and another way you can write it is as AB, as capital letter AB with a stroke above it showing the direction or the path taken by that vector. General equation or representation of a vector. Vectors are completely written as this is, for example, A. This is the vector which is equals to the magnitude or the absolute value of that vector times the lowercase of a subscript a, or simply the same thing here but without the subscript. So what this means is that this is a vector which is defined by its magnitude here and its direction. The lowercase a, which you remember I said is unit vector. Now what unit vectors are? They are the vectors that show direction, so they are sometimes called directional vectors. And as the name implies, a unit vector has a magnitude of 1 and the direction is the direction of the vector they define. And so expanding further, the magnitude of A is denoted by this, while unit vector is denoted by lowercase of that vector. So if here were to be capital letter C. Here will be absolute value of capital letter C times lowercase of C, yeah, times lowercase of a subscript C. Yeah, so here are two vectors, but they are different because one is going in clockwise direction, the other one is going in the other direction. And you can see that when a vector changes direction, it causes the unit vector to take on a negative or the opposite sign. So when this vector was moving from A to B and all of a sudden direction changes, then it means it's moving from B to A or negative of A to B. Addition of vectors. Quite simply, when two vectors are added, for example, we have A plus B, the summation or the addition of A and B is given by C. So when you have only these two lines, A and B, you would have to just close this diagram by adding a dotted line or a full non-dotted line to denote the summation of the two vectors. So, and it's quite simply C, which is the summation, is equal to A plus B. It's straightforward. And to help you draw your diagrams the right way, I put this little note here, meaning that when you're adding vectors, the vectors, for example, A will move in the same direction as the other vector, then the summation will move in the opposite direction as the two summing vectors. Take note of that so that you know how to draw the arrows of your diagram properly. Magnitude of vectors. When vectors are at right angles to each other, it is easy to find their magnitude just by applying Pythagoras theorem. So when we have two vectors A and B at right angle to one another, or to each other rather, here is the magnitude, which is R, and by Pythagorean theorem, R squared is equal to A squared plus B squared. So to find R, which is the magnitude, you have to find the square root of the right hand side. The rectangular or Cartesian coordinates representation of vectors. So in free space, we have the three coordinate system, three axis system, x, y, z. This is three-dimensional, and we have ax, which is a unit vector along x-axis, ay, which is the unit vector along y-axis, az, which is a unit vector along the z-axis. So in Cartesian coordinate representation, we would show our vector as ax, ay, az, which is equal to this. Take note of how it's written. See that? Plus this, plus this. Each of these are called components of a vector. So this whole stuff is the representation of vectors in rectangular Cartesian coordinates form, and the magnitude would be given by the square root of ax squared plus ay squared plus az squared, following Pythagorean theorem. And furthermore, since a vector is completely represented as A is equal to the absolute value of the vector times the unit vector, whenever I want to find the unit vector, if we're asked to find the unit vector, quite simply make it subject of formula this way. The unit vector is equal to the vector itself all over its absolute value or its magnitude. So the vector itself in Cartesian form is given by the whole of this all over the magnitude, which is the square root of each of its components squared. Let's move over to position vectors. Position vector or radius vector of point P is a directed distance from the origin O to P, and it's denoted by R subscript P. So the position vector is equal to OP, which is origin, distance between the origin and any points P within the Cartesian coordinate system, and is given by this vector here. So a position vector is given by this vector. What it actually means is when you have any point whatsoever points anywhere, the point could be here, could be here, could be here, could be here, anywhere, you will have to just trace where the point meets each of the axes. So since this is a point right here P, you trace where it meets the Z axis, where it meets the Y axis, and where it meets the X axis. The intersection, which is this place right here, will give the position vector. Hope you understand that. Then when we want to solve position vector problems, this diagram is going to be of help to us, because this is how it is being orientated. So we have distance P to Q. Say we have this distance P to Q. And the position vector RP is this, and this is RQ. To solve some position vector problems, you might be given each of these parameters, and you must learn how to write the formula or the equation, which is this: RPQ is equal to RQ plus RP. It's very straightforward. It's just the addition of vectors as we did before. Somewhat in that manner, not totally the same way as that. Remember what I told you about how addition of vectors went, and this is not the way I explained it. So for example, if we have a vector A is equal to 8as minus 3ay plus 4az, and B equals to 3ax plus ay, we are asked to find the component of A along ay and the magnitude of 5a minus b, the unit vector along A plus 4b. Then let's solve. For the first question, the component of A along the axis AY. Oops, I'm sorry. It's a mistake right here. It was AY, not AX. Yeah, I just made the correction now. So the component of A along AY is capital letter AY. So a way to look at this is seeing the components which we're asked to find as magnitude. So component of A, which is this whole vector along AY, is -3. See that? Which is a scalar number attached to this direction. The second question says the magnitude of 5a minus b. So first of all, we have to find 5a, which is just multiplying our vector 8, -3, 4. You see, just take you back for you to see the comma notation, representation of vectors, and the complete Cartesian or rectangular representation. So 5a would be 5 times a, -3, 4, which is equals to 40, -15, 20, minus b, and our b is 310. This 0 is because AZ has no magnitude, so it's 0. We now perform our subtraction operation, which is 40 minus 3, 37, -15 minus 1, -16, 20 minus 0 is 20, and that would be the magnitude of 5a minus b. Now to find the unit vector of this, we simply perform the unit vector operation by using the unit vector the magnitude. We were actually asked to find the magnitude of this. We just solved for 5a minus b. This is not the magnitude yet, so we are still on the second question. So to find the magnitude is what is going on here. It's 37 squared plus -16 squared plus 20 squared, and it all boils down to 45. That would be the magnitude. It's a single number. To find the unit vector along a plus 4b, we'll just say let a plus 4b equals to c, and we perform the summation of a plus 4b by first multiplying 4 and b to get 12, 4, 0. Then we add 8 plus 12, 20, -3 plus 4 is 1, 4 plus 0 is 4. The unit vector along C is given by this expression, which is gotten from the representation of the vector C. So C would be the vector itself all over the magnitude. Remember that C is the whole of this. So in other words, a plus 4b is equals to this all over the magnitude of a plus 4b. You find you simplify this to give you 20 plus 4, 2. Then you now divide this a common denominator, so 20 all over 20.42, comma 1 all over 20.42, comma 4 all over 20.42. That will give you 0.9794, comma 0.0490, comma 0.1950, 0.1959. Sorry. And AC, which is the unit vector we're asked to find, will then be this. That's when we write the full form of the vector in rectangular Cartesian system. Vectors can be multiplied in two ways. Scalar multiplication and vector multiplication. Scalar product of two vectors is called dot product. Scalar product of vectors or scalar multiplication is also known as dot product because a dot is used in representing this operation. So this is the dot we're talking about here. The scalar multiplication of A and B would be A dot B. So if we have the vector A and B separated by this angle, the scalar product of A and B will be given by A dot B is equals to AB cos theta, and is just projection of A, that will be A times projection of B on A. This A times projection of B on A, or B times projection of A on B. This statement right here is not very important. In order not to confuse yourself, just stick with the formula for the dot product. A dot B is equals to AB cos theta. So if we have a vector, two different vectors, I don't know, this page is not complete, sorry about that. We have two vectors A and B, A given by A1I plus A2J plus A3K, and B given by B1I plus B2J plus B3K. The scalar multiplication of dot product of those vectors will then be given by A dot B is equals to vector A dot vector B. And if you expand this brackets, we have that A1 B1II, that is A1 B1 I dot I plus A1 B2 I dot J. You understand? So you just expand this as you would any normal brackets. Then you will have the whole of this expression. If you want to simplify it further, we have to reduce the whole of this expression by substituting the values of all of these. First of all, what is ijk? Ijk is nothing but unit vectors. This ijk is another way of saying ax, ay, az. So you can either say I, or you could say ax. You could either say j, or you could say ay, and you could either say k or say az. Either way, ijk are unit vectors. Lowercase ax, lowercase ay, lowercase az are also unit vectors, depending on your choice or textbook you are reading. So here, I, since they are unit vectors, remember unit vectors have magnitude of 1, so that's why we have 1 everywhere. I would be 1 times 1 cos the angle between the two vectors. And the angle between I and I is 0 because we are assuming that I and another I on top of it, that would be an overlap or parallel. And when we have two parallel lines, the angle between them is 0. So this I dot I, which is a scalar multiplication, is equal to AB cos theta, which is A is 1, the magnitude of I, B is 1, magnitude of I again, cos theta. Theta is the angle between both of them, and in this case it's 0 because I and I are on the same plane, which will give parallel, and parallel lines don't have any angle difference between them. When you perform this operation in a calculator, you have 1. Same thing goes for j dot j, 1, k dot k, 1. In other words, you could say ax dot ax, which is I dot I, ay dot ay, which is j dot j, az dot az, which is k dot k, is equals to 1, as we had. Depends on your choice of alphabets or representation. Then in the same vein, when we have two different unit vectors, in this case we had the same, in this other case here I dot k different, I dot j different, j dot I different. So is these other cases we are trying to simplify or work out here. We have I dot j, it's still I, which is 1, magnitude of any unit vector at all is 1, times j, which is 1, cos the angle between I and j. And what is the angle between I and j? It's 90 degrees. Because when we have vectors in free space or in three-dimensional plane, we assume that the angle between each of these planes is equal to 90 degrees. That's why we say that the angle between I and j is 90 degrees. When you perform this operation on a calculator, on your head, get 0. So same goes for all of this, 0. What does that tell us? We'll see it. That tells us that wherever we have I dot I, like here, we substitute it with 1. Wherever we have j dot j, we substitute it with 1. Wherever we have k dot k, we substitute it with 1. Then wherever we have I dot j, or j dot k, k dot I, automatically becomes 0. That's why I cancelled it right here. And here, and here, and here, and here, and here, they'll all go because they are going to result into 0. So the whole of this boils down to a1 b1 I dot I plus a2 b2 j dot j plus a3 b3 k dot k, meaning this. But since I dot I, j dot j, and k dot k are all equals to 1, you can see that they will all go as well, because 1 multiplied by each of these would still give this. So at the end of the day, the whole cumbersome equation has reduced into a1 b1 plus a2 b2 plus a3 b3. So that is the formula for scalar product or dot product of two vectors. And in real problems, you see how easy it is to solve. For example, if a is equals to 3i plus 4j plus 7k and b is equals to 3i plus ij plus 3i plus 1j plus 5k, then a dot b would equals to a1 times b1 plus a2 times b2 plus a3 times b3, which is quite simply, which means you should just multiply this and this, this and this and this and this. Forget about the unit vectors, because after performing the dot multiplication, they all become 1. So in scalar multiplication, we are going to have a scalar result. When we move over to vector product of two vectors, otherwise called cross multiplication, it's very similar to dot multiplication. The difference is it's denoted by this symbol, which is the multiplication or cross symbol. So a cross b is equals to ab sine theta. In the case of dot multiplication, we had a dot b is equals to ab cos theta, but in this case it's sine theta. So that is just the difference between cross multiplication and dot multiplication. So unlike scalar multiplication, vector multiplication is not commutative, meaning that a cross b is not equals to b cross a. Rather, b cross a is equals to the negative of a cross b. Again, if we have two vectors a and b given by this and this, a cross b would be the whole of this. Remember how we opened the bracket, so assuming there are brackets around here and here, and you just expand the brackets, you get this. Exactly what we had the other time. The difference is the cross multiplication here. In the other case, we had dot, 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 dot. Since this is a cross multiplication, we'll have cross, cross, cross all through. Well, if we were to simplify further, I cross I will be 1 times 1 sine 0. Remember, the angle between the same unit vectors is equal to 0. So sine 0, we are going to have 0, 0, 0. In the case of dot multiplication, we had 1 all through here, while in the case of cross multiplication, we're having zeros. So in the same vein, well, not in the same vein per se, when we are finding the cross multiplication of two different unit vectors, it's going to give us a third unit vector in the Cartesian coordinate. For example, I times j is equal to k, j times k is equal to I, k times I is equal to j. Meaning that if you multiply these two in the cross multiplication sense of it, you'll get the third element in the Cartesian. Multiply j and k, you get I, which is the other third element of the three-dimension rectangular Cartesian coordinate system. If you want to visualize it with the cyclic permutation, you see that ax times ay equals to az, ay times az is equals to ax, and az times ax is equals to ay. So that's exactly what I have here. The whole of this is the same as the whole of this. Remember, it's just differences, your choice of alphabets or what you choose to represent your unit vectors. So what happens if direction changes? Here we have the clockwise direction. So when we have an anti-clockwise or counterclockwise direction, you see the direction of the arrows. It has changed here. Then negatives will be introduced in our answers. For example, I times j equals to be negative of j times I. This is so because vector multiplication is not commutative. So going further to simplify our vector multiplication, you see that these elements having the same unit vectors will cancel because they'll all become 0, 0, and 0. While in the case of scalar, they were actually the ones remaining because they gave 1. In this case, they will be gone because I cross I is equal to 0, j cross j is equal to 0, and k cross k is equal to 0. We're now left with these other components, and due to the length of this video getting too long, I don't want to show all the workings and all the reductions that went on. All you need to know is that it all reduces to this final form, and it might look intimidating, so fret not, for in real problems a much simpler method is used. What is that method, you might be asking yourself? So the simpler, more straightforward way of solving cross multiplication problems is that we use determinants of a matrix to easily and straightforwardly solve cross product problems. So when we have the same two vectors a and b given by this and this, to find your a cross b, you simply find the determinant of a and b, introducing the unit vectors right at the top of your determinant. These unit vectors will be part of your calculation, and of course you have your polarity of the determinant matrix. And if you solve it, you see that taking this part out, you have this. Then taking this part out, you have this. Then taking this part out, you have this, which is exactly the same thing as we had if you go through the longer route or route. So you can see that using the matrix, determinants of matrix method is straightforward and very simple. Let's solve a problem, shall we? For example, if we have two vectors C and D given by this and this, then C cross D is nothing but the determinant of all C's and all D's, taking into account their unit vector paths. So substituting what we have in our equation, we have that 2, 2, negative 1, which are all components of C, then 3, negative 6, 2, which are all components of D, will now give us that C cross D is equals to, perform this, you get 4 minus 6, negative J, 4 plus 3 plus K, negative 12 minus 6, then which boils down to this. So you will notice that when you are solving a cross multiplication problem, it will give you a vector. So meaning that a vector multiplication will result into a vector. Like in this case, this is a vector. Then a scalar multiplication will result in a scalar, meaning that when you perform a dot multiplication or dot product, the answer will give you a scalar. Finally, before I leave, to find the angle between two vectors, we employ the formula of dot product or scalar multiplication, which is a dot b is equal to ab cos theta. So quite simply, when you're asked to find the angle between two vectors, you just make the angle theta the subject, which is equals to the inverse of the cosine inverse of the dot product all over the absolute value of AB. And that's it for now. Make sure you like, share this video, comment, and also subscribe to this channel. Thank you for your patience for sticking through this whole long tutorial. Catch you next time. Bye.